Okay, I'll start with a little bit of revision. Maybe this switching of these lights might be better because this place is getting overglowed. Can you switch off these two lights? No, I don't think so. It usually creates a problem. Okay, fine. Is it visible, online audience?
Yes, sir.
Okay. Okay, so what we will do today, we will, yesterday's class was kind of washed out because there was no internet connection there. So I will do a little bit of revision. It cannot do too much of revision, but if this kind of problem keeps happening, we have to, like we should write formally to IT to fix and all that. So anyway, so we'll do a little bit of revision of the basic principles of quantum mechanics, and then we will talk about, we'll start with some ideas of symmetry, which is something also I discussed yesterday, and then we'll go to the deeper aspects of gauge theory. Okay, what is a gauge theory and how it works? Okay, so and let's since we lost some time, let's not waste any more time to discussing about the general outline of the course. After the class is over, I'll have a little chat with you to tell you what is the structure of the course and all that. Okay, so the basic notions of quantum mechanics is quantum mechanics, first of all, is a projective theory. Is a projective theory. So this is just for the benefit of the new people, those who took quantum mechanics 1, my quantum mechanics 1 at least, we extensively discussed. I'm sure you also learned it in your quantum mechanics. So just to revise it a little bit. So what does it mean by projective theory? The main content, the main object of quantum mechanics is states. Now the state is a wrong word, not a good word here, because normally by the English word state implies it's you describe an object about its property, right? But there is nothing like that exists in quantum mechanics, because you know that you cannot definitely tell about the property. So what a state actually does in this case, a state is a prescription in quantum mechanics. A state is a prescription of what you can get when you measure. Right? What are the possible outcomes with what probability? That is what a state tells you. And they are represented by rays. Again, I'm putting quote unquote rays because rays are basically projective vectors. In other words, they are basically, this is a mathematical name of projective vectors. Projective vectors in complex Hilbert space. Why? Because why they are projective? Because we know I can represent a state by some C1, let's say C1 alpha plus C2 beta. Let me call it 1 and 2, C1 1 and C2 2. But it's a perfectly good description if I multiply the C1 by some e to the power I gamma 1 and C2 e to the power I gamma 2. Some arbitrary phase I can multiply it with, and I also can multiply with an arbitrary global phase. Nothing changes. So what is the simple colloquial meaning of rays? Rays means something, rays are like a vector of unit amplitude whose directions doesn't matter, magnitude also doesn't. Magnitude is fixed, its direction doesn't matter. And what matters? Its relative direction with respect to another state. Okay? That is what matters. So that is what gives you the interference and all. So this arbitrary global factor doesn't change anything. For example, when you look at this Stern-Gerlach experiment and all, there we did 1 by root 2 plus z, 1 by root 2 minus z. Now I could have put an arbitrary phase factor here and here. Nothing will change. What matters is square of this object. Square of this object is the probability that you actually measure. The probability amplitude, this factor is called probability amplitude. That doesn't matter. So that means what? It's like a two-dimensional vector which has two components. But if you arbitrarily change the factor, that means another vector is also good enough. As long as you have these two things, which means these numbers are intact, whose square you are going to measure. Okay. But what matters is that if you have another vector, then how you choose the first one, that will matter. So relative orientation will matter. Why? Because if I have another vector phi, which is, let's say, d1 1 plus d2 2. Then what is the probability of getting phi along psi? Then you take inner product, that will be c1 times d1, right? But they will, then the phase will matter. Then if you have an arbitrary gamma phase or beta phase, then they will start to matter. Okay? So that's what means that the vector's direction and amplitude is fixed, direction doesn't matter. But what matters is relative direction with respect to another vector. So these things are called projective vector. Quantum mechanics is an entirely projective theory. And most importantly, these states is a wrong notion of word, which is, as you know, that in quantum mechanics, we didn't invent a new vocabulary, but we just transported all the vocabulary we had in English language and applied it here, and all meanings changes, momentum, etc. meanings starts to change. State also, the meaning changes. So in classical mechanics, what do you mean by state? State, you say, okay, x and p. You measure x and p, that describe the state of the particle. It means where the particle is and what is the momentum of the particle. But here you are not saying that. You are saying the particle could be here, and they are actually at these and these both at the same time until you measure. And when you measure, you will find it one of them with a certain probability. So the meaning completely changes. And this thing is called realism in philosophy, which tells you that what is the state of a certain object that doesn't depend on whether it is observed or not. That is the philosophical meaning of realism, and realism is broken in quantum mechanics. So this is the first postulate of quantum mechanics, that everything is described by states, and states are a projective vector in a complex Hilbert space of unit amplitude, and states doesn't describe the state as we use in the English language, but it rather gives a prescription of what you can find when you measure, and it is in both of these states, in fact, at the same time. So this is the first statement of quantum mechanics, first thing that we learned. And the second thing we learned, then there are corresponding things, that is superposition, that tells you, which gives you all this strange idea that these can be in two states at the same time until measured, and we discussed all these interpretation for that, like many world interpretation, and then trying to explain it using you all have heard about the cat demonstration of Schrodinger. The cat is dead and alive at the same time, and all that. Okay, so now the next thing is, this is what actually brings a direct bridge between quantum and classical, is the concept of operators. So the state in quantum mechanics has no correspondence in classical mechanics. It's completely a quantum concept. The state means quote unquote state. Okay, this state, not that state. What you understand the word state in English language. So operator is something that is the one which actually bridges. So they are basically observables. States are not observable, but states are a prescription that tells you what you might find or what you can find when you measure an observable. So what are the observables? Anything that you measure, that momentum, position, spin, etc., anything can be observable. So what we learned, that observables are represented as state. Why? Because when you perform a state, you convert one state into another state. One state vector becomes another state vector. We gave the example that if I take a state psi in a Stern-Gerlach device, it goes in either plus z direction or minus z direction, which means you convert one state k into another state k, which means the observable or operator must be an object that convert one ray into another ray. What is that object? That object is a matrix or operator, the object that converts one vector to another vector. Okay, so they are represented by matrix or operators, and they has to be Hermitian. Why? Because we want, what do you want? Why Hermitian? Real eigenvalues. Okay, but there is a very interesting point, that there exists a whole world of non-Hermitian operator. So this is also something you have to done. We are cooking up the mathematics as per as we need the physics, but that doesn't mean that's the only possibility. So there is a lot of discussion nowadays. It's a very interesting branch where you can get, so Hermitian matrices are not the only matrices that can give you real eigenvalue. Non-Hermitian matrix can also give you, and that's a whole branch of study. But in quantum courses, we don't go there. Okay. So let's say I want it to be Hermitian. Whenever a measurement is involved, you want the operator representing that a Hermitian matrix. Okay, because a measurement is involved. So now comes also the point of measurement, and we also came with the notion of expectation value. That tells you if you do many measurements, since it's a statistical theory, if you do many measurements, then it's statistical but deterministic in the sense that you can predict the probability, not the probability individual event, but the probability. If you perform many measurements, then what number you get, you can also find it knowing the states. Okay. So these are the idea of operators. Now operators are the objects that connects with you to actually classical mechanics. So then we have we name them as per classical mechanics, but still they are very different from how things are in classical mechanics. Okay. Then as you learn operator, then two concepts came. Then these are concept of compatible and non-compatible. Compatible and non-compatible. Which means if two operators commute or not. Since they are matrices, mathematically we can immediately imagine there are classes of operators that commute or not. Now this is a conceptually new concept in quantum mechanics that doesn't exist in classical. That what do I measure? If there is a measurement is involved of two operators, then what I measured before and what I measure after matters. Commute means what? AB or BA, they are different, right? And we learned this through the Stern-Gerlach experiment. So let's say we learned this example. It is like, let's say I have two kind of balls. These balls are red and black and white, or they are square or round. Okay, two kind of property: black, white, square, round. So if I pass and they are equally mixed in a box. Okay. Now if I pass through a filter that separate color, you will get 50% black and 50% white. Now let's say I take only the black and pass it through a shape separator. I get 50% round, 50% square, right? Because they are all equally likely. Right? But now this is all what we expect in classical mechanics. Right? But now if I take the shape and take this guy, pass it through a color, what do I expect? 100%. All of them I expect them to be black, right? But we know that if these two properties, the color and shape, if they are non-compatible, then you will again get 50% black and 50% white. Of course, we know that color and shape are not compatible observable. So if you do this experiment with color and shape, you will not get this. But spin X and spin Y, or spin X and spin Z, if you do the Stern-Gerlach experiment, Sx, Sz, Sx, then you will get this peculiar result, because spin observables, they don't commute. Okay? This is the property, and this particular property also, this is very important. I am not going into the details, that if two operators commute, which means if A be 0, then they have simultaneous eigenket, which means you can represent the eigenvalue, they label the states with their common eigenvalues. And that is what we do in hydrogen problem. We call them SPDF orbital. They are basically common, they are basically eigenvalues of the operator that mutually commute. Okay. Now this is basically what we learned about operator. Then the third thing we learned is dynamics. Now before dynamics, we also learned about one important concept, that is continuous transformations, which means if you transform a state, so how can you get one state vector to another state vector? You either perform a measurement, then it becomes project into one, and then you represent that by Hermitian operator, or you can transform them from one place to another. This is called spatial translation. Or you can transform them from one time to another, then it's temporal translation. And we learned that such continuous transformation has a generator. Always continuous transformation has a generator. They satisfy certain properties, that's called Lie algebra and Lie group. And we learned extensively about it. For example, if you do space translation, its generator is momentum. If you do time translation, its generator is Hamiltonian. That's why the Hamiltonian is a very important object. And we learned that if I translate a state from some initial state to some final state, we do it by applying this operator. This is called this is a operator that applies the time translation. It takes a state from a particular point of time to another point of time without any measurement. Okay, this is also very important. If there is a operation that doesn't involve a measurement, that doesn't need to be Hermitian, but it has to be unitary. Why unitary? Preserve probability. It must preserve something that is probability. So psi t must be equal to psi 0, psi 0. Okay. So this was how we constructed dynamics, and we learned I can write an infinitesimal version for this because it's a continuous transformation. Continuous means I go from this to this, t equal to 0 to t equal to t. I can divide this space by infinitesimal chunks and can take limit to 0. And when I do that, I can get a differential form, which is the celebrated Schrodinger equation. Now, this is an interesting point. How many of you know this? Let's see. So, can I call this thing an energy operator? You, Gogula should not answer. You took my course, you know that. How about others? Yes. Okay. Now, do you think Schrodinger was a stupid who wrote energy H psi equal to H psi? Why did he write a whole equation if that is the whole point? Right? If this is the energy operator, then this equation is a tautology, right? It says H psi equal to H psi. Why did he took that much effort? Why that much fuss to write H psi equal to H psi? Okay, the point is you cannot call this an energy operator. Why? Because if you call this energy operator, so this is again, I will refer to you some lecture in quantum mechanics 1. You will see that you have to, so for example, if I have xp, these two, this is a translation and this is the generator of the translation. So p is represented as I h bar del del x, right? You know that. And xp satisfy I h bar. So can I do th where h is I h bar del del t, and therefore a th is I h bar. So turns out you cannot play this game. Why? Because if you do that, then you have to allow a room for infinitely negative energy. Why? Because these two operators, they are observable, so they are Hermitian operator. So they must have a completeness. They must have a complete set of states. Now that means if t goes from minus infinity to plus infinity, h must also go from minus infinity to plus infinity, which is not a problem for x and p. But if you allow energy to go to minus infinity, that means there will be no stability in any system. A system, if it allows its ground state and energy can go to minus infinity, such a system will never be stable. So in single particle quantum mechanics, you cannot do this. You cannot write this. So therefore, this is not an energy operator. It is not. It's basically time. It just says that it is psi t plus del t minus psi t by del t limit del t goes to 0. It is just what derivative means. It's just an infinitesimal version of this equation. It is not h psi equal to h psi. Okay, because there is no time operator. Time is a parameter in quantum mechanics. It's not an operator. But there is a catch. The catch is it's only true for systems where you cannot imagine a negative infinity energy, right? But that is not true for relativistic systems and many body systems. There you can allow time as an operator, but that leads to various problems. So what you do is, now relativistic system says you have to treat time and space equally. So instead of calling time an operator, you call time is a parameter and space is also a parameter. And that is what you do in field theory. Okay? Space and time both are treated as a background parameter. Okay, just to revise that the main point is this: dynamics is given by this. Okay. Now you can imagine all the transformations that I can do, all the things. So for first thing, this is already a transformation that states can acquire a arbitrary phase factor that doesn't change any of the observable physics. Okay. So now you are already getting an idea. Quantum mechanics is also a gauge theory. It's like you can do a transformation that doesn't change any observable physics, and you can similarly for here also you can have an arbitrary phase factor here and here that doesn't change any of the physics. So let's see how that plays out. Okay, everybody got this revision point, and everybody knew about all this, even if you have not thought about this, but somewhere you heard this. Okay. Okay, good. So this is revision of quantum mechanics 1, the basic idea. And of course, we are using this idea everywhere. Even the differential Schrodinger equation is basically this equation where the differential is an infinite by infinite matrix. The object you write as this. I am not allowed to go this side probably. Too little board it is. So we learned this form, for example, minus h cut square by 2m del 2 del x2 plus vx psi x equal to v psi x, right? So this is basically an infinite by infinite matrix. You can imagine this as x minus h cut square by 2m del 2 del x2 plus vx x prime psi e x psi summed over x prime, right? So this is basically all the Schrodinger equation form is nothing but this. There is one more point I want you to think if you have not thought about it already. You must have seen there are two equations, right? One time dependent and time independent Schrodinger equation. You have never encountered such a thing before. When you studied Newton's law, you didn't have to. When you studied Newton's law, you didn't have a time independent Newton's law and time dependent Newton's law. Why is that? This was actually an interview question for some. Okay, think about this. This is because there is a peculiarity in this form. So the Schrodinger equation is not a wave equation. It's a wave equation, sorry, it's a wave equation, but it's a strange kind of wave equation because it has two derivatives in one side and one derivative in other side. Okay, so think about this. Why do you need two equations? When you have equations of this form, then this structure appears naturally, time dependent. And this is not only in quantum mechanics. Where have you seen this kind of equation? When you studied waves in optics, it was not like that, right? Because there it was del 2 del x2 psi 1 by c square del 2 del t2 psi, right? That was the wave equation of optics, right? But have you learned heat equation, heat diffusion, heat? So heat equation has this kind of a one derivative in one side, two derivative. That's why many techniques from heat equation are used in quantum mechanics. Okay, many techniques like diffusion, Monte Carlo, and all that are used to solve quantum mechanics problems. Okay, look up a little bit about all these. These are basic stuff. Revise a little bit. Okay, now let's talk about. Let's talk about symmetries. So all the online students, although you have learned this, I hope it is on top of your head right now. And if not, make sure it is. Okay? And you can ask the people here. We ask such questions in interviews. Okay. So now let's talk about symmetries. So what is symmetry? Some of you. Yeah. What? Why you talk about that symmetry out of all the symmetries in the world? What is symmetry in general? In a very common sense language. Yeah, you do something to an object and nothing changes. right? That is symmetry. So it turns out, so this is the notion of symmetry in classical mechanics, okay, in classical physics. So it turns out in quantum mechanics there are three kinds of symmetries. Two of them are directly correspond with quantum mechanics, classical mechanics. One of them is only exclusive to quantum mechanics. So what are they? This is usual. Let me call it usual, transpose, and gauge. So gauge and usual are also there in classical physics. Gauge symmetry is very profound. I'll talk a little bit about it. But transpose is a special to quantum mechanics. So what are there in usual? They are usually of two types. One is linear, and another is antilinear. So linear one, by linear and antilinear means they are represented by linear operator, Hermitian, linear, unitary operator. Antilinear means anti-unitary, anti-Hermitian. Any of you have experienced anywhere anti-unitary operators? Those who took quantum mechanics 2 in their MSc. Did you study time reversal symmetry? Any of you? Or forgot? It's okay if you studied and forgot, but so you can tell that. Okay, how come you none of you studied quantum mechanics 2 with time reversal and all? You studied but forgot. Okay, that makes more sense. Now earlier I was judging your university. Now I'm judging only you. Okay, okay, good. Okay, so now no, that can happen because you go somewhere else after there and then you say, oh, you didn't study any of this. Then they will judge me, but better they judge you. Okay, so linear are basically the one which we will actually learn linear antilinear here in this course. This is the content of in quantum mechanics too. But linears are basically of two types. One is continuous, and that is discrete. So the continuous one you have learned amply, like translation, all the rotation, right? They are like represented by some kind of a operator, its representation, all these generator, everything. Like of course, continuous means they have a Lie structure, which means there will be a generator, angular momentum for rotation, and linear momentum for translation. Now discrete is, for example, space inversion or mirrored symmetry. Some system can have a mirrored symmetry or space inversion symmetry. Then that's a discrete symmetry. Right? That's the one you are talking about, x minus x. It's called parity. Okay? So now that is not a continuous, therefore it doesn't have a generator. Okay. Now there is a class of symmetry that is antilinear, represented by anti-unit. So we will learn about this later in this course, and we'll also learn about antilinear. So this is what we learned in quantum mechanics 1. Okay, so these are always discrete. An example is time reversal. This is quantum mechanics 2. Any of you know what is time reversal and why do we care about it? Because we are not going to reverse time, right? Then why do we care about such a symmetry exists or not? Even in classical mechanics, right? We talk about time reversal. Let's say Newton's equation. The Newton's equation, if I put t to minus t, nothing changes. Why? Because there is a 2-second derivative in time. And that's we also experience. For example, if I throw a ball and it comes back to me, and if I reverse that movie, then you cannot distinguish, right? You can just flip the motion at every point and you get back the same thing. But of course, this is another interesting point to notice. I will talk about it again later. Although time reversal is not disallowed, like time reversal in other words, say when we sometimes we use the, like if you watch this movie Tenet, I don't know how many of you watched. So they use the time reversal in that sense, like you drop a egg, it breaks, right, and it comes back. But that cannot happen because of probability. It's not dynamically ruled out. It's not a ruled out motion that if you put a scattered piece of egg, it can come back. But it's probability. It's like monkey typing Shakespeare kind of probability. It is improbable, but not impossible. But anyway, so Newton's equation naturally has time reversal. So any dynamical equation of motion, you expect it to have time reversal. But Schrodinger equation doesn't have that. Why? Because it's single derivative in time. If you put t to minus t, it acquires a minus sign. But hopefully it is not a problem because a minus sign is nothing but a pi phase, e to the power I pi phase. But we already argued that a phase is not important, arbitrary global phase. So we'll see that. We'll try to understand. Then from there the whole complication comes. How do you set up the time reversal in quantum mechanics? Okay. Now in transpose, there are again two type of things, linear and antilinear. And one example is charge conjugation. We will not learn it in this course because this transpose symmetry generally comes in many particle setting. So this is charge. Some of you must have learned about CP violation in particle physics and all that, and in quantum in condensed matter also the electron hole symmetry, right? Electron and hole, but you cannot have a concept of a hole unless there are many particles filling some Fermi level. Then you remove one object, right? So that's why we will not discuss it in this course, but just know that this exists, the charge conjugation. Then comes the gauge symmetry. Now gauge symmetry is not a symmetry of nature, but it's a symmetry of description of nature. So we'll try to understand what does this statement means. Now you have came across, all of you have came across some gauge symmetry somewhere, right? Electrodynamics, right? Classical mechanics also you must have came across. Okay. So gauge symmetry are of two types, continuous and discrete. So continuous is the one in classical mechanics. You see, you can add this arbitrary factor that vanishes as a whole derivative in the Lagrangian. But in quantum mechanics, the general one are U1, SU2, and SU3. If you think of U1 is electrodynamics, SU2 is weak interaction. This is QCD, and this can be SU2 cross U1, for which Glasow, Weinberg, and Salam won Nobel Prize. That is for electroweak sector. Okay. Now discrete, these all appears in particle physics and also in condensed matter physics in various contexts. The discrete appears only in condensed matter physics, like Z2 symmetry. And you must have heard somewhere or read somewhere, the mediators of these are bosons, right? Gauge boson, gluons and photons. So photon is a gauge. So you will learn that in QFT, not here. So they are usually boson, and for discrete symmetry they are fermion. The mediators are fermion. There is no discrete symmetry, gauge symmetry in particle physics, but in condensed matter both kind of examples are there. Okay, so this is basically an overview of symmetry, and we will now talk a little bit about gauge symmetry. So how gauge symmetry appears in electrodynamics, then I will tell you how it comes in quantum mechanics, then I will give you a bigger example that how it appears in economics. Okay, gauge theories are everywhere. Okay, and this is also generally my notion that whatever you do, whenever you can apply certain ideas that we call physics, that is also physics. So that means economics is also physics. Okay, so let's see. There is a person called Eric Weinstein who is a physicist, later turned economics, and uses gauge theory to predict various economic models. Okay, you will see it's a very generic idea. It's very generic idea. It appears in many contexts because it's not a symmetry of a theory, but it's not a symmetry of nature, but it's a symmetry of description of nature. It's a formalism symmetry. So we'll see. So what is gauge symmetry? We have learned in ED that these are the Maxwell's equation, rho by epsilon naught curl E. What was the other two? So this was the four basic laws. We know this is Gauss, this is Ampere, this is divergence, and this is Faraday. Okay. So you can see the whole board, online audience, right? Okay. So then there is another force equation, which is Lorentz force. This is Lorentz, and the continuity equation. This is the whole electrodynamics. Okay. If you like compact notation, then you use this F mu nu, which is del mu nu A, and you can write this whole in terms of F. If you like differential geometry, This is the notation of the whole Maxwell equation is written in this one line in differential geometry. Okay. But anyways, so the point is it is all these things. So now where is the gauge symmetry here? Somebody, you know this, right? Online audience can also tell. What? Why are you so silent? Forgot or never knew? So gauge symmetry is the idea that B is curl A and E is grad phi minus del A del T. So you can express the electric field and magnetic field in terms of a potential. Okay. But by the way, how many of you think that potential is a no, not how many of you think. What do you think about potential? Is it a real? Is it the real thing or it's a construction to help you? Construction. Okay, very good. That is what we learned. But here we will see in quantum mechanics, it is the real thing. Okay, it is the real thing because we will see that there are scenarios where a particle is passing through a region of space which has no field, no force, but some potential, and then that is a measure. It brings a measurable change in the particle. Okay, so we will learn that. So of course you know that in the whole formalism of quantum mechanics, we use Lagrangian and Hamiltonian, right? We never used force, right? And force we are, and it's also true in the whole Hamiltonian Lagrangian formalism. We don't need to think about force, right? We can only think about potential. But you all learned it's a construction, right? It's a construction like money, or right? Money is a construction. It's not a real thing. It measures value of something, right? So, but it turns out it's more than that in quantum mechanics, because we know a psi t is e to the power minus IHT psi 0. So which means if you take a particle, pass it through a region of space, because you know, for example, if V is constant, force is 0, right? There is no force. So if you pass it through a region of space of constant potential V1 and V2 and do an interference, then they will pick up different phase, and that phase will be observable. Okay, the interference pattern will shift, but there is still a little bit of cheating here because these V1 and V2 are different. That means there is a force somewhere in between, right? There is a gradient. So I will show you an example of using a solenoid in somewhere in the next class, that if you use a solenoid, you know, in a solenoid the magnetic field is only in the middle, right? There is no magnetic field outside, but the vector potential is all over outside, right? Did you do this problem, chapter 5, Griffith? Okay, revise this. Okay, if I have a solenoid, how do I calculate the magnetic field? So this is the magnetic field, let's say. How do I calculate the potential if this is the magnetic field, the vector potential? The vector potential, you will see it is all over outside, not inside. Although if the solenoid is infinite, the magnetic field is only inside. You can show that if a particle passes through this, it acquires a phase. That phase can be detected in a interference experiment. Okay. Again, it has to be compared with another particle, another path which doesn't have that phase. Okay. And that means potential is the real thing, and we'll see that here. But anyway, so right now we know that potential is a construction, A and phi, and then there is an object. We can transform this potential. Now, if I have a set of electric field that is described by a potential phi and A, this is not unique. Okay, there is another phi prime and A prime which is equally good. Why? If and which A prime phi prime? If this is connected to this by this. If it is connected to the old phi and A by this gamma. Okay, you know about this, all of you. You know, you are completely expressionless. You know this, or you are finding it? Okay. Okay, good. So all of you know that this is gauge transformation. Gauge transformation means what is measurable, that doesn't change. Potential is not a measurable. Okay. So now let's see what does it mean in quantum mechanics. Then what will be that object in quantum mechanics? Now it is obvious to you that State is not measurable, right? State is a prescription. What is measurable? The probability. So therefore, the same object, same role must be played by the space factor. Okay? So let's see. Okay, one more thing which I told last time. So I hope all of you know this. So let me quickly state it here. Can you write down the Hamiltonian of a particle in electromagnetic field? I told you how to write down the force, right? Do you know how to write down the Hamiltonian? If you know the force equation for something, you should also know the Hamiltonian, right? How do you write that? Any of you studied somewhere? Okay, revise this. I believe you did, you forgot that E is what? E is del phi del t, right? B is grad A, curl A. So write E as del phi del t and B as curl A. So now this is obvious. So force is minus some potential, right? So you have to bring it in this form, grad of some scalar, right? How will you do that? The E is already in this form, but the B is curl A, so you have to do B cross curl A, right? Now you know the back cab rule, right? A cross B cross C is basically, this is the back cab rule of vector multiplication, is B A C minus C A B. This is the back cab. Apply the back cab rule here. It will come to this form. It will come to a form of minus grad V. So what, do that, and when you do that, you will find the following: that the Hamiltonian for a particle electromagnetic field will be half mv square kinetic energy plus potential energy, and the V will be plus q phi minus q v dot A. That V dot A will come from this back cab rule. Okay, this is the Hamiltonian of a particle in electromagnetic field, and you can also write it in a one more compact form, and that is given by a half mv square. You can also write it by p square by 2m. So this thing becomes half p minus qa plus q phi. Okay, 1 by 2m. So do this little exercise. I am sure you have done this, but might have forgotten. Okay, so this is important. Why? Because we know that there is a simple way to get a quantum Hamiltonian if you know the classical Hamiltonian, by putting a hat on all the observables, right? You have used that earlier. So this is actually another interesting point. There is no sane way to find the Hamiltonian of a system. In all problems you have done in classes, in courses, you are given, okay, this is the Hamiltonian, find the spectrum, find this, find that, right? But in real world, you don't know actually the Hamiltonian. What you know is some measurable, right? You measured something, and that also you never measure energy. What you measure is energy difference, it's transition, right? Then how do you find the Hamiltonian? So this is a very challenging problem, and this is itself a problem, that how to figure out the Hamiltonian, and there is no science in it. It's art. It's complete pure art. You have to guess the Hamiltonian in various one way or the other. And I will tell a little bit more about how one can guess the Hamiltonian. In fact, there is an article somebody read. So either beg, steal, or borrow the Hamiltonian. There is no sane way to get the Hamiltonian, and it's itself a problem. But some problems we know, where we know the classical counterpart. We start with the classical problem, then we put hat and get the Hamiltonian. That is one way, and it doesn't always work. For example, if I think of a spin system, spin doesn't have a classical counterpart. How do you construct that Hamiltonian? That's a very interesting problem. The whole magnetism is all about spins. Okay, so now let's and also go more deeper. Standard model, all these WZ boson, leptons. Where is their classical counterpart? So it's a very interesting problem. Just know that problem exists, and then let's go back to this. So now in quantum mechanics, what is the gauge transformation? In quantum context, gauge transformation is defined to be change in the phase. Okay, which may or may not, which may be, let me write, may be local. So I'll tell you in a moment what do I mean by local, but this is generally called. So if the phase is global, then it is just called global transition. So it simply means I have a psi xt which I transform as e to the power I alpha xt. So this is my transformed one. Okay, right is equal. Now, if this is global, which means a constant, then it is called a global transformation. So this is global, and this is local. Local means it depends on space time. Okay, so this is what it is. Now, I will give you a little exercise which I will discuss in more detail in next time. So now let's ask the question: if I apply this gauge transformation, how the Schrodinger equation changes, right? Our expectation is our dynamical rule, the relation between quantities, that should not change if I apply a gauge transformation. So first do the simple thing, do the global. What is the exercise? So x1. So take this. Right? So now put everywhere, replace the psi by psi tilde. What will happen? You have to take a derivative with respect to that. Now you can imagine if alpha is independent of x and t, nothing will change. Okay? Can you see that already? Online audience, can you see this? Are you there or you ran away from the class?
Yes, sir.
Okay, very good. Okay, so now try this exercise. First, alpha is global. Now, then do alpha local. Now, if it is local, then a lot of problem will come. Why? Because now you have to take a time. It's you have to do chain rule basically, right? And take a time derivative of this and space derivative twice for this. Okay. So do this exercise and you will find the following. We'll do it next time. We'll talk about more detail about it next time. I leave it as exercise now. Del psi del t. If you replace, if you do this, replace by tilde, nothing will change if it is global. If it is local, this will be simply same as del psi del t. But if you start with this, you will lead here. To show this, that if you add this, you will get this derivative in alpha and time derivative in alpha, which is obvious already that of course there will be a derivative in alpha and time derivative in alpha somewhere. It will come in this form. But that what does that mean? That means Schrodinger equation is not invariant with respect to a local phase transformation. Okay. So then what is the problem? Why it is like that? So what to do about it? Okay. Now it turns out in this form, if you do the following transformation. So now so this is what happens to Schrodinger equation. So the conclusion is Schrodinger equation is invariant but Schrodinger equation is not invariant with respect to a local gauge. not gauge, let me call it phase. If it is not invariant, then I cannot call it gauge. Okay. These are the two conclusions. Now, what is interesting, it turns out if you introduce electromagnetic field, which means your Hamiltonian is this. If this is your Hamiltonian, then this is your equation. If this is your equation, then if you do this case transformation, if you do this transformation, you can show that if you do psi xt goes to e to the power I alpha xt psi xt, but you also take phi xt to phi xt minus del alpha xt del t axt plus 1 by q grad alpha xt. If you do these two transformations also, you can absorb the extra terms that appears because of the local gauge transformation. Okay. So try this exercise. I will show it in detail next time. But the main point, the conclusion is the local gauge symmetry. If you want local gauge symmetry, equation demands presence of E and M fields. Now this is the really non-trivial result. Okay. It means that if you have Schrodinger equation without electromagnetic field, you don't have a local gauge symmetry. But if you demand local gauge symmetry, then you also have to have electromagnetic field, which transforms accordingly, which transforms by absorbing this alpha, which comes because of the alpha phase factor. It is like the lambda in the earlier classical notion. Okay. So this is where I will. Okay, there is a little bit of time, 2 minutes. So I will talk a little bit, so I will show you the algebra in the next class. But you can try it yourself. It's very simple, just taking some derivative. But everybody got this point, what I'm saying? Okay, now we'll talk more about what is the implication of that, and it will happen in many other cases also. Like if you have Young-Mills gauge transformation, like SU2, you will require the electromagnetic forces, and similarly other things. It also happens in case of gravity. For example, in case of gravity, what you say, you have a curved spacetime, and if you demand your equations to be invariant in that curved spacetime, you will require the force of gravity, just like this. Gravity is also a gauge theory. Okay. So now let me talk a little bit about what are gauge symmetry and how does it come in a how does question of symmetry comes. Okay. So I'll give a little bit of hint. I'll give you a train of thought, and I want you to think about it. Okay. We'll discuss it in detail again in the next class. So let me give you an analogy. So let us say I have a grid. Okay. I have a grid where each vertex is a defined country. Each vertex in defined country, and I give you a game. I give you a set of rule. So let's say this example is, so let's say this country has a currency peso, this country has a currency dollar, this has a currency rupee, and no, rupee notion is this rupee, and this has a, what is pound? This is pound. Okay. And each they exist in a grid, and the grid is connected. These countries are connected by some bridge. Okay. Now there is a conversion rate of currency between two countries. Okay. So the conversion rate could be, let's say, 10 peso is equal to $1, like $70. Sorry, $1 is equal to 70 rupees, right? And like similar, 80 rupees is £1, and so on. Like some conversion rate is there between all this. Okay. Now you can think this conversion rate as some interrelation between variables. Okay. This is a very ideal model. Actual economics is much more complicated than that, because every country can be connected to every country. So then it is a very complicated problem. So I'm just saying this is, let's say, the connection. And you want to understand sometimes what happens, that if some country goes through a strong inflation, they change the unit of currency. So I don't know if you recently read all this. So this year Argentina won World Cup, right? So people talked a lot about situation of Argentina economy. Their economy is highly inflation prone, and so much inflation prone that in 1960, whatever they called 1 peso is now 10 to the power 13 peso is equivalent to that. So this is the rate of inflation. So when this kind of crazy inflation happens, sometimes a country resets their unit of money, right? For example, now we start to, let's say, call 1,000 peso is equivalent to one. They change the currency. If you look at their actual currency, they put a stamp on that. It's called Australis. So 1,000 peso is now one Australis. You can also say, okay, let's say India have a huge inflation, and you started calling 1,000 rupees as 1 rupee. You redefine, the scale is reset. Okay. So then please, if your salary is 50,000, it now become 50, okay, in the new scale. So what is important, that such a transformation should not change anything. Rich, whoever is rich will remain rich, poor will remain poor. There will be no economic opportunity and nothing will change. Okay. So this is an example of a gauge transformation, where you are resetting the gauge, the measurement or the unit. Okay. So let's say now such a thing happens in one of those countries. So that means the interrelation of things change. Okay. But then what should not change? So now let me ask you. So let's say somebody travels from this country to this, like this, in a circle. So now the rule is this of this travel. At this bridge there is a bank, and whenever it travels, he converts his currency from whatever he had to a new currency, and so on, right? Now you can try to play this game, and you can see that is it possible for a person to gain money by doing that process, by earn money just by traveling and converting. Okay, it turns out you can. Now it should not change whether the person is making money and how much money he is making just by traveling. It should not change by these local scales transformations. Okay. Now this is the same thing happens for electromagnetism, where each point is like each point in space has a local U1. So you can think space as discrete, space-time as discrete, although it is not discrete, it is continuum, where each point has a U1, a circle, an imaginary extra dimension, an imaginary circle. So this U1 means where are you on this circle? Okay, where are you on this circle? That should not change anything. Instead of a circle, you have a sphere if it is SU2, and so on, if it is non-abelian and all that. Okay, so this is roughly the idea. So I will elaborate this example in much more detail in the next class, but I want to leave you with the interesting thought that gauge theory is much more the idea of gauge theory or gauge symmetry. So again, then why did I call you symmetry? Why did I bring it in the form of symmetry? Because I am doing a transformation here that changes nothing. Right? That's why it's a symmetry. Now, how that symmetry affects what we do, that we'll see. So this is the idea, and yeah, that's all for today. That is all I wanted to say. Online audience, anybody there? Any questions? They ran away for lunch probably. Okay. Okay, good. So that's the formal class is over here. Now I want to give a little more. I want to talk for about 5 minutes just to tell you that the logistics of the course. So before, any questions at this point? Okay. So I would say, okay, so now let me tell you a little bit about the logistics of the class. I can stop the recording. Those who are not there in the